Hi everybody, welcome to another video in Discrete Math section 1.7 Introduction to Proof. Before we begin, if you haven't seen proof before, this might be difficult, but just like the title says, it's just an introduction. It just introduce some common technique that we can use to prove things. I will not go over this. If you want to, just pause the video and read it. I just want to start with the definition of some things here. So a theorem is a statement that can be shown to be true, so we have to prove it. Whereas definition, axioms or postulate, definition, those things we don't have to prove. But the theorem we have to prove. A lemma is called a helping theorem or result that is needed to prove a theorem. So that is before we have a theorem. And corollary is the result which come directly from a theorem. So this is what we have after a theorem. Less important theorem are sometimes called proposition, something that we only need to use for some specific reason. And a conjecture is a statement being proposed to be true, so we don't know if it is true or not. This is to be proved. So those are all the terminology that we need to know. Right. So if we say it, if x greater than 1 for every x and y positive real numbers, then x squared greater than y squared. And the point here is that for many theorem in this section, it's home for all the elements in the domain, and so the domain should be specified here. Right. So let's go over some method of proving things. The first one is the direct proof. So we prove it directly. So we start with P is true, and we follow a bunch of different other rules, and then we say Q must be true. So that is the process directly proven. Right. Now, before we prove something, we need to have some lemma, like some helping theorem, or definition or axiom, something that we can base out reasoning on. Right. So the integers n is even. So if n is even, then n can be written as 2 times k when the k is an integer. Right. So if 2 times something, that's going to be even. If n is odd, that's going to be 2k plus 1. The plus 1 here make it odd. Right? The 2k is even, plus 1 is odd. Of course, if you have an odd number plus 1 that's even, then plus 1 you have an odd, just alternating like that. Right. Now the proof here, give a direct proof. If n is an odd integer, then n square is odd. So we start with this. Of course, if we want to write properly, we said for every n that is even. Of course, you don't have to write all of this. Just write the important. There's this k such that. Right, so important here is if it is even, it's going to be 2k. Right. So the part that we really need is the part in red. Those are bare and which, so we really don't need that. If it is even, we say if n is even, it is equal to 2k. But of course this is odd, right? So start again. For every n is odd, there's this k such that n equal to 2k plus 1. n is odd, then 2k plus 1. Now we just need to square it. This is algebra, there's no trick behind this. I'm just going to multiply it out. 2k plus 1 times 2k plus 1 so 2k, that 4k square plus 2k plus another 2k plus 1. Now that gives us 4k square plus 4k plus 1. Right. How do we know if it is odd? Well, here we can just group the first two terms that have k in it and factor out 2. And they'll say, why don't we factor 4? Well, we don't, because we don't need 4. We only need 2. If this is 2, then we have 2k squared plus 2k and then plus 1. Because it is in this form, this is a number 2 times a number, so this whole thing here is even plus 1, so this one is an odd because of an add 1 here. So we prove it. If n is odd, n squared is odd, right? Like I said, the important part is here, all of the other things. It's nice to know, but we really don't need that. Right. Next, prove that the sum of two rational numbers is rational numbers. Well, rational number is defined to be anything in this ratio form. Right. So anything in ratio is fraction, is rational numbers, right? So we said, usually we can write like that, or we can say let a over b and c over d be rational number. And then the sum, so a over b plus c over d. Right. Usually when we add fraction, I just want to write a part that is more important. A over b plus c over d. When we add fraction, we multiply by the common denominator, right? The common denominator, least common denominator is going to be bd. So we have b already, we just multiply d top and bottom. Then plus, and multiply b top and bottom. So we have bd at the bottom. We have common denominator, so we just add them. Right. It is in the ratio form, so therefore this one is a rational number. So we start two rational number, we add them, we have another rational number. Of course, if we are not given that, of course, that might be difficult. If we're not given this definition, it will be difficult. And the next one, prove that if n is an integer, treat n plus 2 is odd, then n is odd. Right. And the guy here, the helpful hint here that we need is this, we use contrapositive. So let's write the contrapositive for this. If this is a statement, so contrapositive. we have to flip the statement and then negate it. So n is odd, so we say if n is, we have to negate it, so it's not odd. Then 3n plus 2 is not odd. Right. Of course, that's what the contrapositive. If we rewrite not odd meaning even, right? Or we say if n is even, of course the not odd here meaning even, then 3n plus 2 is even. So that's equivalent thing to prove. All right. Usually when we prove something not, is more difficult. Something like if we write like that, it's difficult. So we convert to the meaning, the actual meaning. Right. Now if n is even, right? So that's where we start. N is even, meaning there exists a k such that n is equal to 2k. And now we substitute in here. Then 3n plus 2 equal to, now the n, I'll just substitute n equal to 2k. Give us 6k plus 2. Now, we need to show that this one is even. The 2, of course, is even. We can say 2 times 3k plus 2, right? The reason we need the 2 here, because multiply 2, multiply something, that makes this one is even. An even number plus 2, so that's still even. And so that's all we need to prove. Usually when we're done proving things, we just say QED. So that is a Latin word of that we need to show. And I mean that's what we need to show. And so usually when I was in school, they said this quick enough, done. Right. Now next prove that if for n if n square is odd, then n is odd. Right. So how do we prove this? Now think about this. If we have to prove n square is odd, we start from n square equal to something. That's not really easy to show that, right? But we say that when n is odd, if we start from that, if we start from n and we make something more complicated than n, that will be easier, right? So with that, let's start. If we start from this, if we say n is something, then we'll make more complicated things easier. So again, I will write a statement that we need to prove. If n square is odd, then n is odd. So write the contrapositive. I'll have to flip this and negate. If n is not odd, then n square is not odd. Which is equivalent to n is not odd, meaning n is even. I should say if n is even, then n square is even. And this is what we need to prove. Run backward like this is easier to prove, because if n is even, we know where we start from there. N is even, meaning that there exists k such that n equal to 2k. Right, and then we just need to know what is n square. That gives us 4k square, and then we can split out a 2. When we say 2 times something, that make it even. Right, so that's what we need. So sometimes it's more difficult to write, to prove directly, switching around using contrapositive. This is easier to do. Right, so next, proof by contradiction. To prove P, we assume that it's not P and divide the contradiction such as P and not P. So this is an indirect proof. So like I said, if you haven't seen proof before, this might be difficult. But usually we just assume that it is something is not true. And then we're going to show that. That's one. It follows that the contrapositive is also home. Alright, so we just follow this trend. Alright, let's just jump right to it. Prove that if you pick 22 days from a calendar, at least 4 must fall on the same day of the week. Right? So, let's say, and the proof by contradiction is, suppose that is possible. We said, suppose we pick 22 days and it is at least 4. So opposite to at least 4 is, so the proof by contradiction is we assume that it is not true. So suppose that we pick 22 days, but only in 3 weeks or less. Now we show that this is not possible. Right, now let's see, if we have 22 days and there are 3 weeks, so we can divide the days into 3 weeks, right? Or we said we divide the 22 days in 7. Why do we divide by 7? Because there are 7 days in a week. And that is 3 with remainder. And apparently this later on we is known as the pigeonhole principle. Now think about this. You have 22 days. Doesn't matter what you pick. And then we have the slot. Mondays, Tuesday, Wednesday, Thursday, Friday, Saturday and Sunday. Do 7 days. And you have 22 of them, right? 22 days. let's say we just slot, you can pick 3 for it, but that's only 21. You still have one more day left, and doesn't matter what you put in here, one of them have to hold 4, right? So this is called the pigeonhole principle. If you have the holes and all the pigeons fly into it, and if each hole can hold 3 pigeons, there was one extra one that stand outside. When it fly into it, it will have at least 4. So that's why I said at least 4 must fall on the same day of the week. So when we do like this, it is not possible. So that's why this is not possible. So it has to be 4. Right? So we left 1 remainder is equal to 1, which is not possible. So this is not possible. So it has to be the other way around. That is true. So the other one must be true, meaning if you have 22 days, it must fall in, at least one of them must fall on the same day of the week 4 times. Right. So now use the proof by contradiction to prove that square root of 2 is irrational. All right. Irrational meaning not rational numbers. So, and that's what we try to prove. So proof by contradiction, we assume the opposite to that. So suppose, or we say assume square root of 2 is rational. So assume to the contrary that it is rational. If it is rational numbers, it is written as a ratio, right? We talk about this. Now, the crucial part of this is not just assume that it is ratio. It has to be the ratio that is reduced. Assume that this is mn, which is reduced. And that is very important part in the proof. By the way, if it is not reduced, we can always reduce. For example, by reduce, I mean 4/6 can reduce to 2/3. So we look at the 2/3 and not 4/6. Look at the reduced fraction. Right. Now, square both sides. So that gives us 2 equal to m squared over n squared. Now cross multiply, we have 2n squared equal to m squared. Now, I said, what is the significance of this? Now the thing is, if n squared and m squared, if it is reduced, meaning that they have nothing in common, they cannot reduce anymore. So if we have m squared and n squared, meaning that there is something to reduce. M squared, if you write m squared over n squared is not reduced. Because it can reduce to 2. Right? So meaning that m and n is not reduced. Which is opposite to, which is a negation of what we assumed earlier. So because this is contradict to what we just make, so square root of 2 must be irrational. So we assume it, but it did not work because there's contradiction that led to contradiction. So that's why it did not work. Right. So it is easy to see for some example. For example, 2 over 3, if we square top and bottom, if this is reduced, the square is still reduced. Because if there's nothing common to simplify, when do squared, there's nothing common to simplify. So that's why we say m over n squared is not reduced, there m, that means m over n is not reduced. So that's what we have. Next, prove that there is no largest prime no largest prime numbers. Now this is difficult. Where do we start? Right. Now, this is more like the proof of that by system. We just need to show that it doesn't matter. So assume to the contrary. So suppose there are only finite prime. And let's call them P1, P2, P3 on the way to Pn. But wait, let me define what is the prime number. Prime number is the number that only divisible by one and itself. So 2 is a prime. Maybe some example would be nice. 2 is a prime. 3 is a prime. 4 is not a prime because 4 is divisible by 2. 5 is a prime. 6 is not because 6 divided by 2 divided by 3. 7, not 9, not 8, not 9. So those are prime numbers. Right? Now, if let's suppose that we have those prime numbers. Now we construct this. So this is proof, not contradiction, but more like construction proof. So here we said, if we take P1 times P2 times P3 times on the way to Pn. So if this is the case, this is the factor, each factor of them. So this number divisible by P1, divisible by P2, divisible by P3, and so on. What we do is we're going to add 1 to it. But just this little trick, make that it's not divisible by P1, P2, P3, or Pn. So because of that, it has to be prime. This has to be prime. Right, for example, if you take the 2 prime, 2 and 3, and then you plus 1, that's 7, that is a prime number. Or take 2 times 3 times 5 plus 1, so that 2 times 3, 6 times 5, so that 31, that's also a prime number. So by plusing 1, make it not divisible by any of the prime numbers that we know. So in that case, we say that have finite prime, we just find 1 more. And then we just keep adding 1 more. Each time we find it, the number will get bigger and bigger. So that's why there's no largest prime. And also there's prime, infinite number of prime. So there is no largest prime. Right. So those are some nice classic proof. Right. Now let's look at something that is not a proof. Right, so we look at this, it said proof that 1 equal to 2. You know there's something wrong here because it's not true. But it builds some very convincing. Suppose A equal to B. Right, that's fine. Because A equal to B, we can multiply A on both sides. Yeah, that's fine. And then subtract B squared on both sides. That's fine. That factor, that's okay there. And divide. We get back to that. If you divide by A minus B on both sides, we have that. And then because A equal to B, so that 2B equal to B divided by B on both sides, right? So of course somewhere along the line this is not true, and the part is not true is this, because if we divide by A minus B, that is the problem, because if A minus B, since A equal to B, A minus B equal to 0, we cannot divide by 0 because divide by 0 is undefined. So here we divide by 0, so that's why this is not a proof, because we cannot divide by 0. Anything divided by 0 is undefined, so we cannot do that. So that's why this is not a proof. And the final note that there will be a lot of different strategy, but usually the proof we take some creative way to prove. But of course we'll study more of that in the later chapter. But for now, I'm going to stop at this point for section 1.7. As always, thank you for watching and see you in another video in Discrete Math.